Hello, my name is Ariel Martinez, and this is my Lab 4 presentation, Oscillations. So in this presentation, I'm going to give a small introduction to the lab, talk about my procedure, my tracker setup, initial conditions for my code, show my model code and my graph, then discuss the differences between the observations in the model, discuss what the data means, and then different methods of getting the oscillating periods. So as an introduction to the lab, we were examining the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. The two forces acting on the mass are the force of gravity and the spring force, which can be shown here. So the spring force is negative k L minus L naught times L hat, and the force of gravity is negative mg. And obviously our net force is going to be gravity plus spring force. So using Newton's second law, we can find the velocity and position iteratively and plot the position and velocity. And also using the energy principle, where energy is equal to kinetic energy plus potential gravitational energy plus potential spring energy, which is going to be a net equals 0. So the procedures for this lab, we uploaded the provided oscillating spring mass video to tracker, set up initial conditions, and plotted the position over time data. Then using these initial conditions we derived from tracker, we created a computational model of the motion using VPython, plotting position over time as well as energy changes over time. And then we compared the observed data from tracker with the computational model from VPython, and then analyzed any potential reasons for differences among the two. And so this is my tracker setup. We can see the video in the middle of the rotating spring mass system. And on the right we have the X and Y data over time, and then as well as a graph of the data. So some initial conditions for the model, the graph, sorry, for the code. So the mass of the ball was given to be 0.402 kilograms, and the position of the ball was derived from the tracker data. So as the initial velocity was just a 0, and the spring constant was derived from the period of the tracker data. So using the period, we were able to derive for the spring constant. And then as well, the L naught was also given to us in the problem statement from the tracker data. So using these initial conditions, this is my code where we iteratively define kinetic energy, potential gravitational energy, and potential spring energy. Then we get the force of gravity, force of spring, and then net force, adding these two up. Then we update velocity, update position, update the new length of the spring, and then update all the energies. So we have kinetic energy, delta potential energy, potential gravitational, then change in potential gravitational energy, then potential spring energy, and then change in spring energy, and then as well as the total energy, which should equal 0. So this is a model of my graph, a graph of my model, sorry. So we have the plots of energy, so the red end and green lines are potential gravitational and spring energy respectively. Then the blue line is kinetic energy, and the orange line in the middle is just the total energy, change in energy, which we can see is 0. And then on the right we have the visualization of the spring rotating with a curve plotted and the blue lines in the bottom. So this is a comparison of my observed data from tracker versus the model that was created on VPython. So we can see that the red line is a more realistic, the real actual observed data. We can notice how the data is more jagged and crooked and not 100% smooth, the way the blue line is, which is the observed data, but generally they follow the same pattern, oscillating up and down, obviously positive position. And so what does this all mean? So the biggest question we need to ask is whether the energy principle is satisfied by the model. So the energy principle states that change in total energy is equal to external work done on the system. And so since there are no external forces acting on the model, we would expect change in energy to be 0, which is in fact depicted by the model as shown by the orange line in the first graph. So as we can see, this orange line here, which stays as 0, change in energy is 0. So the energy principle is in fact satisfied. So under these initial conditions of the model, the energy principle is satisfied. So now looking at oscillating periods, there are two potential methods of deriving the spring constant using the period of the oscillations. We could have used the X position data or Y position data. We can see that they were slightly different. So the total period using X position data was derived to be 1.5836 seconds, whereas using Y position data, one period was derived to be 1.456 seconds. So because of that, the spring constants using X and Y position data would be slightly different. So for a Y position data, they would be a slightly higher spring constant. And so for my calculations, I simply used the x position data, but really I think either could have been acceptable.